I'm the daughter of two PhDs in electrical engineering. Both of my parents, after World War II, went off to Madison, Wisconsin and studied electrical engineering. Actually went there on the GI Bill. My father's straight out of the military, and my mother having done a sort of a gig as a Rosie the Riveter, working at an electronics company during the war. So I grew up with two technologists as parents. I had an older sister who, before me, was studying math, computer science, and became a very successful technologist and serial entrepreneur in Silicon Valley. So when I came of age, I was really attracted to the idea of designing things and inventing things, and doing that in the context of technology and even things closer to computer science was like falling off a log. Yeah. I went to undergrad at Berkeley and then went to MIT for grad school. And in grad school, and particularly during the time of my PhD, I was part of a systems group. And Dave Clark was in that systems group, still is, research scientist. And he was one of the main people who really built the IETF. And that was the organizing body, still is. But in the early days was the organizing body that was where people came together to agree on, to create, to test and iterate on the protocols that made up the internet. So I had, coming out of grad school, this interest in internet development and such. I ended up at USC as an assistant professor, somewhat coincidentally. Two-body problems. My husband got a position at UCLA, and I got a position at USC, thanks to George Becky, I might add, who was the chairman at the time and just an amazing person and mentor. That was January of 1986. I got there and I started trying to build a systems group, get machines to have in the lab, get graduate students who were interested in building things. I've always been an experimental type of computer scientist. I was just going to academia to try it out, figuring I would end up doing things that were more applied. And at some point, I don't remember exactly, but I think it was Danny Cohen who suggested to John Postel that they might invite me over to spend time at ISI. And that happened, and I think it was in the late 80s. I remember, because I remember this floor, and I remember those Christmas balls hanging on the wall, because my son, who was 3 at the time, was running around the floor and met Danny Cohen's son. And they became the best of friends. I knew about Danny Cohen, this brilliant man who did many, many things with DARPA and many things having to do with graphics and all aspects of technology. He was also the person who really caused TCP and IP to be split into two separate protocols, because he was one of the first people who tried to build real-time voice applications over packet switching. And I'd heard about Danny Cohen as being one of the promoters of Star Wars at the time, the Star Wars Defense Initiative at the time. So SDI was developed to help protect against nuclear attack, to detect an attack and to preemptively respond. The Strategic Defense Initiative, it was at the time of Physicians for Social Responsibility and Physicists for Social Responsibility, and that whole movement that was very concerned about undermining the mutually assured destruction and the whole balance that was somewhat being kept with respect to the threat of nuclear war. And SDI was of great concern because the technology was not what it is today. And the level of errors and unreliability, I would say even today, but certainly then, was of great concern. We had a t-shirt made at the time that said, "It's 11 p.m., do you know what your expert system just inferred?" And it had a big mushroom cloud on it. AI, right, was called expert systems at the time, and that's what SDI was based on, an expert system that would, be able to detect the difference between, a seagull and an incoming warhead. Danny Cohen was one of the minds behind that project. Danny Cohen, to me, I had never met him, was this Darth Vader character, right, who was promoting this technology that I was against. I didn't particularly want to have a conversation with him about it. And he was also known as not suffering fools. And Danny was brilliant, and we were all fools next to Danny. So I was basically scared of him and avoided him at all costs. And then at this holiday party at ISI, our sons met. And basically, I ended up spending probably the next decade every weekend with Danny Cohen, with our kids. And he became the closest of friends and the most loyal of friends and amazing human being. And we managed to never exchange a word about politics. John Postel did his PhD at UCLA in computer science when my father was there. He then moved to ISI, and he worked on early ARPANET work and many early components of applications running on the ARPANET. When I first met him in person and came to ISI, I was a faculty member at USC, but he invited me to become a researcher also with his division here at ISI. So he was head of the networking division at ISI. And to the world, he was the name and numbering czar. You wanted an IP address? You wanted a block of IP addresses? You came to John. And who could you possibly trust with that kind of power? The person you could trust was John. He was selfless. He was completely not political. And he was out to do the right thing for this infrastructure that he so deeply believed in building. He promoted and set an example of a kind of citizenship that is hard to find these days. We don't think of the early technologists as being that kind of citizens. I think John Postel, very much one of those. Another person that comes to mind is Vint Cerf, very much a statesman. And John, in his own way, was that kind of a quiet, humble statesman in the robes of a mountain man. I was a faculty member at USC, an assistant professor still in the late 80s, and I wanted to teach a course on network protocols. And my idea of network protocols were TCP/IP. You didn't bother teaching other network protocols, but at the time I had to justify it. There were these OSI 7-layer reference models and these other European standards that were being proposed. And it was questioned why a course that was teaching the protocols that make up the internet was even being taught. There were not very many academics who did internet and networking at that time. It was really considered sort of an engineering plumbing, if you will. And I really, as with many other people, sat at the boundary between the university and places like ISI, which were largely public domain producing technology, not proprietary technology, not commercializing the technology, but effectively productizing it so that it could be used. So I came to USC. I was relatively frustrated in trying to get system stuff going, and I was alone as opposed to how you are in grad school where you're in a whole group of people. And suddenly I was invited to spend time at ISI. And here were people who were full-time working on building experimental technology and stuff that wouldn't just work in the lab, but that would go out into the field and become part of this grand experiment, which was the internet. Bob Braden, obviously John Postel. They weren't just alone, they were working with a community of the internet research community. Dave Clark from MIT, Scott Schenker, who was at Xerox PARC, Lisha Zhang at Xerox PARC. Xerox PARC was a very close collaborator in all this work, and of course Van Jacobson. I say of course Van Jacobson because Van Jacobson saved the internet from congestion collapse when he introduced the TCP congestion control algorithms into the internet. Without ISI, I wouldn't have been able to enter that world, and it became my world in its entirety. My students, all my work for a very solid decade was spent here in this building where I'm sitting now, and being part of building a kind of infrastructure that is with us today. I often think that if not for ISI, I would have left academia. From around 1986 to the later 90s, the focus was all on the internet research community and the IETF, which is the Internet Engineering Taskforce, where these research concepts really got built into new protocols and new building blocks. I was particularly interested in routing protocols and what were known as interdomain routing protocols. So as the internet grew so that it was not a single administrative domain anymore, how do you build protocols that would work across all these administrative boundaries? And from that, I moved on and worked on multicast routing with amazing people like Steve Deering, also at Xerox PARC, Van Jacobson again, who was at Lawrence Berkeley Labs. And ISI was really the center of where a lot of that research and exploratory work came together. Bob Braden, who was also in John Postel's networking division, ran what was known as the end-to-end research group. And this was the people I mentioned before: Dave Clark, Scott Schenker, Van Jacobson, Lisa Zhang, Steve Deering, the people who were working on the architecture of congestion control, of routing, really the underlying robust architecture of the internet. And it was also amazingly successful that by the late 90s, you had a lot of commercialization happening. There was very little, almost nothing happening in the late 80s. Late 90s, this was critical infrastructure for everybody. There was a lot of commercialization, which had to happen to bring the internet to what it is today. And as a researcher, it became a little harder to do research on those lower level protocols because it was too critical of an infrastructure to people to want to go and try your new multicast routing protocol or your new interdomain routing protocol. It was serious business at that point. So for me as a researcher, I pretty intentionally said, well, it's either time for me to move to industry or it's time for me to start thinking about applications that sort of move up the stack, if you will, up that hourglass. Or maybe I should I really loved being part of designing and prototyping multicast routing. Maybe I should think of other things that need to be networked, not just routers that are part of critical infrastructure. And that was the thought pattern that caused me to start looking into distributed sensing and what is sort of a relative of Internet of Things at this point. So that was just an incredible decade with so much change in the role of the underlying architecture, and ISI was really at the core of that. I got here in that amazing time of this incredible research community building the internet protocols. And as things became more and more commercialized and I wanted to stay in an academic environment and do research that still hopefully would matter at some point, I moved on to do this distributed sensing work. And some years into that, I started in the late 90s on that work and started it here at ISI with John Heidemann, who's on the 11th floor, under the Sense-IT program, the Sense-IT program. So I did this ISAT study, and it is part of what led to a DARPA program, and we started that here. John Heidemann and Ramesh Govindan. Ramesh is mostly faculty on campus now at USC. In doing that distributed sensing work, I became more interested also in the interaction between the applications of that sensing and the underlying infrastructure, because that's the nature of sensing. You're not some low-level packet forwarding router. You're all about the bits that are being monitored in the world, and became increasingly interested in environmental monitoring, both for ecosystem modeling, things like better understanding microclimates and how they are affected by climate change, marine underwater ecosystem modeling, which I continued to do with Gaurav Sukhatme and marine biology colleagues at USC, and environmental monitoring, things like groundwater contamination from agriculture, things like that. All these contexts where there wasn't spatially dense information available about a particular phenomenon. And we were building these architectures of distributed sensor networks that would let us, our tagline was, that would let us reveal the previously unobservable. Because you either had to do hand samples and go and put in a probe and collect the data, or you'd had some very coarse remote sensing information. And we were filling in that gap by building distributed sensing systems. To me, distributed sensing was just another kind of internet architecture. And from there, in distributed sensing, as we were doing that, one of the most interesting form of distributed sensors that suddenly emerged on the scene were smartphones. So all of the phones that we carry around in our pockets have sensors in them, and they are very interesting sources of information about us as humans, as well as being tools that we use. Not planned, but just a transition from internet to distributed sensing, to phones as sensors. And then one of the most relevant things to sense is things having to do with individual health. It was about really dedicated people building exciting, important technology. Not flashy technology, but exciting because of its impact and the architectural principles underlying how it was being built. And its importance, there was a sense of that importance then, even if it wasn't connected to the notion of scale and every human on the planet. The founders of the internet, including the people in this building, they weren't just implementing arbitrary protocols. There was an architecture, there were principles. And there is so much to learn from that architecture and those principles, even if the details of a protocol implementation isn't the thing that you're learning. What you can learn from the design trade-offs and the approach very much is around robustness, about adaptability, end-to-end principle, all kinds of things of that sort. And so when you teach something like networking, you teach about those principles and those engineering trade-offs. And over time, people recognized that, yes, this wasn't just some fly-by-night particular set of details. And then I do remember the first day I saw a URL on a bus, right? So we went from the internet protocols, nobody knew what I was doing at a cocktail party or telling my friends. It was like, they'd ask what I do and I would just say, I would, change the subject because it just wasn't going to make a lot of sense. And then the web happened with Tim Berners-Lee and HTTP. The web was built on the internet, and that opened up what the internet could do and be to people. It opened it up to everybody. It was an infrastructure that would support a wide range of applications. The hourglass describes the internet architecture with a narrow waist. So the internet protocol was the narrow waist of the architecture, and that's the one thing that every device connected to the internet and the routers creating the internet had to implement. They had to implement IP and have IP addresses. Underneath it, you could have all kinds of different technologies, from twisted pair, original telephone lines, moving on to Ethernet, coaxial cable, eventually to fiber optics, and even from the beginning, using wireless and having the IP work over radio links. So what was so valuable about it is that you had a common protocol, but the underlying technologies could evolve in a modular, distributed, decentralized process. You didn't have to turn the whole internet up to be a higher bandwidth at one time. That way of developing a robust architecture allowed for scaling, allowed for heterogeneity, because you can only get so big before you get heterogeneous. You can only get so big before you run out of things that are going to use just this one or two set of applications. So the scaling of the internet wasn't just about the bandwidth of the links and the size of the IP address. It was also about all the things that it could be used for without any centralized control or coordination. Remember, the telephone system existed. So it wasn't the case that there was no communication before it, right? So, but the internet itself was more what we would now call about enterprise use. And it was becoming the basis of how scientists, at least, and then increasingly business and Wall Street and all sorts of industries needed it in order to resource share and get access to real-time information. So when the web was created, the web was also still largely about academics and science, and then it started being about the Whole Earth Catalog and other things that began to grow towards things that were a little bit closer to the average consumer. Then commercial entities started putting out web pages for individuals, and then everyone began to use the web that way. And then, of course, it wasn't until the social media came into play and Facebook was created. I mean, there was social media before it, but really with Facebook, that notion of everybody being on all the time and then powered by everyone having a smartphone on them really turned into that being the outcome. It was about robust information sharing and access to real-time information so you could operate bridges and railroads and really important infrastructure things. People started to talk about toaster-net a little bit, like an early notion of the Internet of Things, right? What will happen when my toaster is connected to the Internet? And as I moved into doing work in distributed sensing, it was sort of looking at, I don't know, having my toaster on the Internet isn't that important, but having lots of distributed sensors and devices could be really valuable to other things. Open source refers to the program that runs your application. And when you buy an application from a commercial company, you don't actually get to see the raw code that's underlying that application. You download an app or you download a piece of software and you're just running that application. But you can't go in and look at the code and modify it and create a better version of it. Most commercial software has at least significant components that are proprietary. That is not open source. Open source means the source code that runs that program is open and is published effectively. Most systems that we use have a mix of proprietary, closed source, and open source. The value of open source is that when there are libraries and things that all these different commercial products are using, all of the users of that open source are keeping it updated. You effectively have a community of companies that are dependent on that open source, and so it gets updated, it gets fixed, security bugs get fixed. And they all use those open source components to help build their end-to-end proprietary systems. So there are two things that were open. The architecture was open, so that the way you define how things interact were not proprietary secrets. They didn't belong to a single commercial entity. They were published, they were co-designed, published in RFCs, these requests for comments, which also is something that began here. They were discussed ad nauseum, and they were prototyped. A phrase that Dave Clark coined was rough consensus and running code. You could design and argue and talk through principles and model as much as you wanted, but until you had running code in the form of a prototype to represent what your design was, it wasn't going to become a part of the internet. And so there was the RFC process where you carefully documented everything, and there was the open source code that was an instantiation of it actually working dynamically in the process. So it's an open architecture you openly define, and then open source you implement and openly represent it. And then that becomes a reference implementation. And all the various companies and competitors and everybody can go off and take it and make it their own. They can do proprietary implementations that maybe are faster or have some interesting hooks or different algorithms for doing packet filtering. But they all conform to the standardized architecture. And what allowed them to get started is having an open source reference implementation. It became the cornerstone for the industry, for commercialization. The internet community and the ethos of what was going on in Division 7, I think, Div 7, in the networking division of John Postel was all about building the basis of this robust internet. And really a lot of that work was happening before anyone was even thinking about somebody making money. This is long before Cisco. The stuff was not being commercialized yet. It wasn't critical infrastructure. It was universities. I'm sure there was a lot going on in terms of DoD and DARPA use and in the context of, with confidentiality and security things that I didn't know about. But in the open internet architecture, that just wasn't the ethos of the time. we've all recognized for decades now that what wasn't designed into the internet were more hooks for security. It was built as an open, trusting infrastructure. When I mentioned before, in early days, some of the vulnerabilities of the internet had to do with excessive traffic over what were still relatively low bandwidth links. And that was this whole problem of congestion collapse. And to fix that problem, the TCP congestion control was just implemented in all the edges of the network so that no device speaking over the internet would blast it with packets. If it encountered traffic, everything would back off. And that's how the internet worked, not by somebody policing whether you were sending too much traffic, but by having built into the software of all the edge devices that perspective of when you encounter traffic, you back off and slow yourself down. That's how we could build the internet at that time, and it operated that way for a long time. But because the protocols were so adaptive and so robust, it also sort of hid the fact that there weren't more real hooks for security to protect against malicious entities. And so the absence of sufficient management and sufficient security protocols, sufficient authentication, really is still a problem to this day. So to me, the internet will always be the collection of routers and the software on the end systems that make the basic infrastructure work. That's the internet to me, because that's the internet that was built here. Then the web happened on top of that fundamental internet, and that started being called the internet. And then social media happened, and that started being called the internet. And then lots of other devices started being referred to as the Internet of Things. And when I think about these edge devices, I think about my glasses talking to my phone and not to your phone. And then my phone is sending data over that underlying internet infrastructure. So I see the layers underneath. I don't see one flat universe of devices. There was this increasing connectivity through email, and then there was this increasing reason to be connected beyond just human-to-human communication, which came with the web. Because with the web, there was content that you would want to get to that wasn't necessarily by talking to a human. It was somebody's posted content. So that reason to be connected, because there was so much out there, so much information, and then with search, information that you could actually find. And then introduced advertising as the monetization basis for a lot of what was being commercialized in the internet. And when advertising was the key to monetization, then eyeballs and attention became the thing that needed to be optimized. At that point, we lost the truth that greater connectivity was greater good. And then out of that, we got our filter bubbles and our misinformation and our disinformation. And so clearly just optimizing for connectivity in numbers and in time, when we just optimize for that, I think most of us agree we've ended up in a place we'd rather not be. So connectivity was an interesting goal and driver in the early days, and then I think became far more problematic. Because the word connected, it's not a positive term. The word connected, we use it back in the psychological emotional sense of feeling connected. That happens to be the same word and same root as being connected to media, but it has nothing, the words don't mean the same thing. So I don't find anything about it surprising. The more you have distancing between human beings, the more you're going to create an environment of loneliness. I don't think it's just about social media and being online. It's also the whole game industry. It's things that are so absorbing that are great and fun and interesting and have driven a lot of interesting technology, but when it consumes so much of someone's day and they're not out in nature or they're not around other human beings, we haven't evolved for that.